you.
I was kind of midpoint in mine. So for those catching this recording, I do apologize. I forgot to hit record on the first half of the meeting presentation. Didn't recognize that till I was 2/3 of the way through. But we'll be picking up here with Pete giving the main topic on minor planet bodies. So Pete, whenever you're ready to take it away.
Very good, thank you. Everybody see the first screen okay? Minor planets and asteroids? Okay, very good. Ross, yep. Ross, give me a thumbs up. Hey, as usual, it's always an honor and privilege to present to you all. My presentation is going to focus on minor planets and asteroids. And the reason I have asteroids in parentheses there, you're going to see a little, basically some changes in nomenclature, the way things are classified. Pretty much most folks go by the formalization that the International Astronomical Union has put forth. And for the most part, most things other than planets and moons and the sun and comets are known as minor planets, but that also includes asteroids, which is a significant subset of that. But anyhow, I'm not going to get into a lot of detail. I'm going to try to cover a lot of different topics with respect to minor planets and asteroids, with respect to basically, this is what I plan to cover: definitions and classifications, naming, properties. Talk a little bit about Cirrus, Vesta, and Bennu as far as examples. Of course, two are, some of the largest, and Bennu is basically one of the smaller ones. And as usual, I try to provide a little bit of outreach or local flavor. The Astronomical League has an observing program focusing on asteroids. I'm also going to talk about some of the work that we do, not so much asteroids, but one of our educational kits that we go out to the schools with deals with meteorites, and you'll understand later. And then I've got one other little side. So, and by all means, if I say something that isn't quite right, just chime right in and say, hey, Pete, and we'll talk about it, because I also like to consider this a little bit of a discussion. I don't mind if you have questions in the middle of the presentation, just yell at me again. If it's a matter of clarification or you've got some other input, I'm always open to that. So without further ado, as usual, some of the panels always block my presentation, so I'm going to move things out of the way. When we talk about minor planets, it's any astronomical object orbiting the sun that is not a planet or not a comet. And that would include moons too, for the most part. We generally include asteroids and distant minor planets. Approximately 1.1 million are known. I suspect that number's higher because it grows every single day. Basically 600,000 numbered and 5,000, 100,000 are not numbered. It's a matter of classification. You can see with these kinds of numbers, it becomes somewhat difficult to keep track of them all, but there is an organization, and probably a couple that do that, and I'll talk a little bit about them too. And out of this group, we include 5 official dwarf planets. Pluto's a dwarf planet. Ceres, one of the first asteroids that was discovered in 1801, not as an asteroid necessarily. I think it was initially thought to be a planet, but over time was classified as an asteroid, and now subsequently has been classified as a dwarf planet. So out of all those, and it's in the main asteroid belt, so it's one of those objects that has been reclassified over time. Terms that have been used: asteroid, minor planet, planetoid, and I'm sure there are others that have been used synonymously over time. But for the most part, I gave you the definition of minor planet and what an asteroid is. Lo and behold, we get some more terminology. The IAU resolution of 2006: all objects other than planets and dwarf planets shall be referred to as small solar system bodies, triple SBs. So I guess that's just, and small is relative, because some of these objects compared to the smallest, the largest and the smallest, there's a couple of orders of magnitude if you want to look at diameters, mass, or whatever the case may be. Continuing on with minor planet, and I'm going to skip around a little bit. A lot of this material, when we look at minor planets, asteroids, triple SBs, it's believed that a lot of the material, basically is left over from our solar system's protoplanetary nebula. In other words, not necessarily a planet that broke up, but rather this is some of the original material. One of the reasons it's driven a lot of the explorations, I suspect, over the past couple of decades with respect to these bodies, especially with respect to the asteroids in the inner solar system. And what I mean by inner solar system, inside the orbit of Jupiter. The Minor Planet Center basically is the worldwide repository for intake and output of information about minor planets and asteroids, positional measurements, identification, designations, computing orbits when the time is available to do that, and discoveries. Physically, I think this operates as part of the Smithsonian Astrophysical Observatory. Harvard University and the Smithsonian Institution run this jointly. Division F of the IAU, and is funded by NASA's Near Earth Object Observations Program grant, part of which, and I think we had a presentation on this, was the Sky Survey.
Yes, the Catalina Sky Survey.
Catalina Sky Survey, yes, it's run up on Mount Lemmon, and that's very much a part of it. And I think it was Carson or David Foles gave us a presentation, and this is one of the reasons, one of the impetus for maintaining the system. It's certainly the Minor Planet Center, is a repository for all asteroids or SSBs. But of course, the critical ones, and I'll talk about the classification with respect to the NEOs, or the near-Earth objects, that are primary concerns with respect to our survivability, our resilience, or whatever have you. With respect to the Minor Planet Center, they have cataloged a little over 136,000 minor planets that are larger than 1 kilometer in diameter. So these are pretty substantial. That kind of object you definitely don't want to see come too close to Earth, or actually come inside of our atmosphere. I would imagine the consequences would be rather dramatic and drastic, and very severe. And this was as of October 2006. So there's been considerably much more work done, and I would suspect this number is considerably higher. Low total mass of all the asteroids. Pretty much, if you take all the asteroids, and primarily focusing on the ones in the inner solar system, their total mass is less than 4/100ths of the Earth's mass. Everyone's seen diagrams of the main asteroid belt between Mars and Jupiter, would think, boy, there's a lot of stuff out there. There is a lot of stuff, but mass-wise, it doesn't really amount to that much. And that's one of the reasons that suggests this didn't necessarily come from a planet that broke apart, or a planet that was hit by another object, but are actually leftovers from the original formation of our solar system. And so that sort of drives that theory. It's not known exactly, but that is the thinking amongst the professionals today. Main belt asteroids are nearly circular in their orbits around the sun. There are gaps in the main asteroid belt between Mars and Jupiter, and these gaps are located in areas where their orbits are basically a fraction of Jupiter's, because it's primarily influenced by Jupiter. For instance, there's a gap where the asteroids basically are existing anywhere from about 3 to 9 astronomical units out, Jupiter being approximately 9.5 astronomical units, and Mars, I think, at about 2.5, roughly. These are real rough numbers. But anyhow, these Kirkwood gaps, and of course, these were discovered by a gentleman by the name of Kirkwood, like I say, are where this resonance as far as the orbital period is established. For instance, if you get to a spot where you have asteroids, and they'd be on either side of this gap, that are roughly take 1/2 times to go around the sun than Jupiter does, there's going to be a gap. Same thing for 1/3, 2/3, so on and so forth. And of course, there are main gaps that are probably a little more noticeable than others. We talked, one of the things that we deal with locally that the club deals with, we have one of the educational kits we deal with, and it's not strictly on asteroids, but rather, let's see, where did my other, oh, I know what I have to do. Not that. There was something else I wanted to show you if I can find the right panel. Oh, I see. It's not going to let me get there because, okay, I'm not going to be able to show that to you, so I won't do it. But anyhow, we have a toolkit that we take out to the schools, and this is one that particularly works well with elementary schools. And it's not particularly on asteroids, but its basis for the information developed is the asteroids, because we know pretty much just about all the meteors that come into our atmosphere, some which become meteorites if they make it to the ground, most of the material doesn't, is sourced from the asteroids. And this is one of the things we try to teach the kids, give them some flavor for it. The reason this particular kit works well with the younger kids is because one of the activities includes pulling out 8 samples, showing them to them, giving them some information on a quick flip book presentation, and let them use a magnet and some magnifying glasses and try to determine which samples out of the 8 are actually a meteorite. Meteorites come from meteors, meteors come from the asteroids. So this is something that has a little bit more of a practical knowledge. If you ever have an opportunity to get involved with this particular kit, there's a lot of good information on it. One of the things that I was kind of surprised about, here again, normally we see the diagram of what looks like, when you look at the solar system, you see a model of it, you see the planets on their various orbits going out to Neptune. And you see the asteroid belt that's usually identified by a lot of dots. And you'll see this in some of the representations I have. And yes, there are millions and millions probably of asteroids, but for the most part, especially the larger asteroids, and I'm going to say down to those that are probably maybe a size on the order of tens or about 100 meters in diameter, for the most part, their spacing is roughly 600,000 miles. And which, sort of gives a little more credence to, there's a lot of space out there. Yeah, the asteroid belt is populated with a lot of asteroids. You saw some of those numbers I gave you, but there's a lot of space between them. That was one of the things I was kind of surprised about. So one of the reasons we don't have a lot of asteroids knocking into each other, at least in the main belt, unless they have some sort of a strange orbit, not following that near circular orbit between Jupiter and Mars going around the sun. So I always thought that was kind of a fascinating little factoid about how widely spread a lot of these objects are. Okay, getting in a little bit into the classification of the different asteroids. And here again, asteroids, minor planet that is neither a true planet or a comet orbiting within the inner solar system. So we generally refer to asteroids in the inner solar system inside the orbit of Jupiter. First, talking about the near-Earth asteroids, those with orbits inside of Mars. Not necessarily, and you can see there's a diagram that explains these 4 different classifications: the Apo-Heli, the Aten, Apollo, and the Amor classifications of asteroids. And you can see graphically with this little diagram on the lower right here, how they vary with respect to, getting into a talk about semi-major axis, semi-minor axis, aphelion and perihelion. Aphelion is the furthest distance from the sun that a given body goes around the sun. And of course, perihelion is the closest distance. So most assuredly, whenever we find an asteroid within either the Earth's aphelion or perihelion, at some point there's the potential for it to cross our orbit. And you can see this graphically presented. Some come real close and don't cross, but we have 2 cases with the Apollos and the Atens where that can occur. And so, of course, those are of major concern to the, organizations like the Sky Center that keep track of these, particularly the near-Earth ones. And there's an example one here. You can see a near-Earth asteroid. I'll explain the naming convention a little bit before, but it's 433 Eros. A mean diameter, of course, there's no set diameter because you can see from this example, it's nowhere near round or even ovals. It sort of looks like the Oscar Mayer Wienermobile. And in this case, the but the mean diameter is 16.8 kilometers. So it's a pretty substantial object. Definitely something we don't want to ever see coming into our atmosphere. Moving on to the other asteroids, we have Earth Trojans. Now, when we talk about Trojans, and a lot of the planets have Trojan asteroids, or I should say they don't have them, are associated with the orbits of these planets. And that's what defines a Trojan. Basically, it shares an orbit and it is pretty much gravitationally locked. With respect to Earth, there are two known Trojans. You can see the designations for both of them and the rough size. 2010 TK7 is 300 meters across, and it oscillates between the Sun-Earth L4 point, which is about 60 degrees either in front of our orbit or 60 degrees behind, basically 180 degrees being on the other side of the sun. And it oscillates between that L4 and the L3 point, which is 60 degrees to 180. So doesn't move real rapidly. I think they move rather slowly, but they can oscillate in that point. This particular one was discovered in October of 2010 using the I misspelled field, I apologize, but the Wide Field Infrared Survey Explorer WISE. Another one, 614, 689, 2020 XL5, has a diameter of a little over 1 kilometer. And this oscillates near the Sun-Earth L4, so it pretty much stays in a fixed location and it'll move slightly. And this was discovered by Pan-STARRS in December of 2020. And the Mount Lemmon Sky Survey, I think, was also involved in an observation just before that. It wasn't verified until after the Pan-STARRS data came in. Similarly, there are Trojans sharing an orbit with Mars. 8 known. I don't have the identifiers for them, and I don't have the locations, but there are 8 known. And going back, remember I said the asteroid belt is, as far as between Mars and Jupiter, is roughly circular. And then there are also Jupiter Trojans. And in this case, there are quite a lot of them. You can see these in the diagram here with respect to Jupiter's orbit going around the sun. You can see there's a high concentration of Trojans, which look to be about 60 degrees behind and in front of Jupiter's path around the sun. And in some cases, the number of the asteroids or the bodies in this particular area are expected or theorized to be pretty much equal to the total number of asteroids in the main asteroid belt. You can see where that is graphically between the orbit of Mars and Jupiter. It looks like a good majority of them are going to be closer to Mars orbit as opposed to Jupiter, understanding that basically you're looking Mars at about 2.5 AU out to Jupiter at 9.5 AU.
So real quick,
Go ahead.
can you go back, Pete?
Sure.
So the Trojans themselves are, when he means gravitationally bound, they will generally reside in the Lagrange points. These are basically balance points of gravity where the gravity of say a planet like Jupiter or the Earth is balanced out by the gravity of the sun. So they both the sun and that planet will tug on it equally, so that they essentially just sit there floating. Though obviously Jupiter, with its tremendous bulk, will have a larger field for the L4 and Lagrange points, which you can see in the diagram below. But all planets, all bodies will have these neutral gravities essentially, which backs up why there would be these Trojan asteroids for all the planets. Although probably too faint for us to detect for Saturn, Neptune, and Uranus because they're just so far out and receive so little light.
Right. Thanks, Connor. And, similarly, it's also expected, and I'm trying to remember, I think in some cases, these are rare discoveries, even Mercury and Venus. I think there were, in my research, I recall reading, I didn't track this down, but a recent discovery of a Mercury Trojan asteroid. Now, these are going to be probably rather rare and rather few in number, similarly for Venus, but they do exist, and Trojans exist likely for all the planets. It's just that the populations are significantly larger when we start looking at Jupiter and the main asteroid belt. In fact, basically these populations are fairly equal. And of course, once we get outside Jupiter, we start getting into, there's more Trojans, but we get into the centaurs, which are the bodies between Jupiter and Neptune. Neptune considered to be the last, the furthest planet from the sun after Pluto was killed by a couple of guys from Caltech, and the International Astronomical Union decided to demote it. But for the most standpoint, these are unstable orbits caused by the giant planets. The material for these centaur bodies are believed to have originated from beyond Neptune on out into all the way out, into the extremities of the Oort cloud, but probably still fairly close, because some numbers, when you look at the Oort cloud, in fact, you can see I have this down near the bottom of the data, believed to extend out to 50,000 AU, which is 50,000 times the distance between the sun and the Earth. So that's a significant amount of space. But anyhow, getting back to the centaur. So like I say, bodies between Jupiter and Neptune, unstable orbits caused by giant planets. Neptune Trojans, number may be greater than the asteroid or Jupiter Trojan population, but that's unknown because these bodies are so far out. Very few of them have been detected, if any, and it's a rather difficult task to try to survey or estimate any numbers out there. And then, of course, the objects that now we start talking about objects way out in our solar system when we have, I consider Neptune on the order of 30 astronomical units away from the sun, approximately. Trans-Neptunian objects at or beyond the orbit of Neptune, so outside the main part of the solar system. The Kuiper belt extending from 30, roughly Neptune's orbit, on out to 50, out beyond where Pluto is. Mostly frozen volatiles, methane, ammonia, and water. Dwarf planets. We know Pluto's out there. There's a couple of others. Quaoar and Maki. I always thought it was make, but it's Maki. Scattered disk and detached outside the Kuiper belt. Of course, the Oort cloud, source of long period comets. And here again, we're not talking about comets because comets aren't included in this, but that possibly extends out to 50,000 AU. The graphic down here just shows, a couple of different asteroids in comparison to some dwarf planets. You see the dwarf planets pretty much near the top, and a number of asteroids and one other dwarf planet, and they do vary widely in size. And you can see that from this graphic. As far as taking a look at the trans-Neptunian objects outside, especially when we start talking about outside Neptune's orbit, you can see there's the potential for quite a lot of matter out there with respect to some of these distant objects. This is just a graphic representation. And this, of course, like I say, goes outside of Jupiter as the trans-Neptunian objects, all the way on out to the far reaches of our solar system. Naming. With respect to, over the years, naming conventions have been developed, and pretty much what's recognized now for the most part. When a new item is discovered, is given a provisional name, which usually refers to the year of discovery and the half month, and that's where you're going to see the notation. And I cannot see it right now because I'm blocking, part of my presentation is blocked. Let's see if I can get that. But you can see the 2002 AT subscript 4, which gives it a little bit more specific with respect to the half month that it was discovered in. Once the orbit of a given minor planet or asteroid has been confirmed, then it's assigned a digital sequence number. For the longest time, 5 digits, in other words, in the 10,000s. Now, since we're well into the 100,000s, it's now 6 figures. I don't know what the estimate is for that to grow into 7 figures. As far as specific names, which you'll see on most of the larger asteroids, and you'll see a couple of examples shortly. Once an object is named, usually it comes from Greek or Roman mythology. Apologies to all my Roman fans and Italians for not capitalizing the R. Then it falls to famous people. For instance, some of these discoverers might name an asteroid in honor of a colleague, in honor of a political figure back in the time when they were discovered. There's also literary characters, discoverers, family and friends, and television characters, although I don't have an example yet, but I'm sure someone may be able to pipe up with one. But supposedly this is how it goes. Most of the larger asteroids are probably going to have a 1 to 3 digit number and have an individual or a character from mythology attached to it. With respect to basic properties, and I'm not going to get into a lot of detail because the properties do vary widely. Radiation environment. For the most part, these minor bodies do not, and I'm talking about the dwarf planets, but the minor planets and asteroids don't have an atmosphere or magnetic field. Some do. And so if there's any radiation, it's going to be subject to electromagnetic radiation from the sun, and any ionizing radiation would probably come from the solar wind. With respect to the optical environment, advantage, disadvantage, of course, they are rather small and difficult to see, but the changing albedo or the amount of reflected light and color can help with the determination, establishing an average magnitude or an apparent magnitude for the body rotational period. These aren't just stationary rocks floating around the solar system. Some of them may actually have self-motion, localized motion, axis orientation, shape, and scattering properties, which will vary depending on the amount of material or the material that's on the surface. Geological, for the most part, I don't think there's any geological activity present or current for the minor planets or asteroids. People will notice impact craters, and a lot, of course, are believed to have been formed. They're basically rubble pilot structures where material in these various regions of the solar system are pretty much coalesced with each other. Magnetic, for the most part, with a couple of very rare exceptions, it's not believed that, with the exception of a couple of asteroids, they have an internal core or a core that has conductive fluid moving. So you'd have the convection, so you'd have an internal magnetic field. Generally, if they do have a magnetic field, it's going to be from a nearby object, or it's a remnant of one they may have had at one time. And these are generally going to be some of the larger asteroids. A couple of examples, of course, here is now classified a dwarf planet, was an asteroid. Like I said, it was discovered in 1801 by Giuseppe Piazza at Palermo Astronomical Observatory in Sicily. Initially, it was thought to be a planet. Over time, then it was determined to be an asteroid when other asteroids were probably discovered. And of course, now it's a dwarf planet, and it is the only dwarf planet known inside Neptune's orbit. It's a middle main asteroid belt, so it's in one of those mid-ranges between some of the major gaps. It varies in its orbit around the sun between 2.5 and almost 3 AU, has a mean diameter, and this one's roughly circular of just under 1,000 kilometers, and its mass is roughly 16 thousandths of what the Earth is. Magnitude at opposition, in other words, when it's on the same side of the sun as the Earth is, when it's best viewed, is about 6.7, and at opposition it will vary down to 9.3. It has a roughly, that's every 15 to 16 months. Of course, in its orbit, it's going to be a little bit slower than the Earth, but so we're going to catch up to it. But if you can imagine, we're at opposition as the Earth starts to race around the sun. Sirius is still going to move off, so it's not going to be in the same position in 12 months, but we catch it again in another 3 to 4 months beyond the year. Not much is known about the surface until the Dawn satellite visited in 2015. It also visited, I think it was Vesta, and that's where we get some of these nice pictures. And a lot more was known about this particular body, believed to be composed primarily of water, ice, and hydrated minerals, carbonites, and clay. Even today, it's believed to be cryovolcanically active. In other words, it's theorized that there may be liquid water below it, and that some of this liquid water escapes in jets, not nearly as dramatic as some of the other outer bodies have demonstrated, but it's believed that some does come out, and it's been observed, and I'm sure that was something that was probably picked up by Dawn. Sort of a rare thing, but being that it's one of the larger asteroids, a possibility. Move on to Vesta, which was the other asteroid that was visited by Dawn. This one is in the, I get this, so let's see. There were 2 point, yeah, this one was on the inner main asteroid belt. 2.15 to almost just over 2.5 AU from the sun, with a mean diameter. This is not, no, well, it's not far, it's kind of far from round, like a football, 525 kilometers. So still a very substantial asteroid. This is interesting. I'm not sure what this word is, but obviously I did not check this. That was probably the month, and I don't know what it's supposed to be, but it was discovered in 1807 by Heinrich Olvers. Like I said, it was on the inner main asteroid belt. Magnitude of 5.1. It actually is more visible to us here on Earth because of its proximity in the inner main belt. And at opposition 5.1 to 8.48, here again, the same 15 to 16 month cycle. And then, of course, 101955 Bennu. Of course, everyone, I think, on the club is probably aware of Bennu and its notoriety with respect to the sample return mission that was accomplished. That was tail end finished. There's still a lot of study, but the sample was returned last year. One of the interesting things, I don't know how many of you got down to the book festival this past weekend, but some of us were down there working the tent, Science City. Of course, TAAA had 3 tables down there, but early, and I think it was Saturday morning, I had a chance to talk to one of the project members before. It was about 7:30 in the morning, about 2 hours before the book festival opened up, and she showed me quite a few neat pictures. Some of the pictures from some of the microscopes. It was some pretty interesting stuff that they found. One of the things, and you can see the factors on Bennu. It is a Apollo, sort of is an Earth crossing asteroid, but I was just one of the things, I think they were expecting about 600 grams of material was the target expectation. They ended up bringing back almost double that, which is kind of interesting and much more substantial than the Japanese sample return mission a year or two, a couple of years prior to that. It's just brought back a few grams. So they had a lot of relatively a lot of material to look at, but it was interesting talking to this a member of the team. They were very, very fascinated, still very, very jazzed about the project, which is now, of course, heavily into the study phase at this point. But you can see the relative size of Bennu. It's only, I say only 490 meters. It's still a pretty substantial asteroid, but in comparison to Vesta and Ceres, it's substantially smaller. And of course, as you get into, there's a lot more that are somewhere mid-range. But this is probably a little bit on the low end of the average size of a number of the asteroids as far as the known ones or minor planets. Okay, one thing I always like to talk about on some of the topics I bring to you is that the Astronomical League has an observation program for asteroids, primarily focusing on the main asteroid belt. The neat thing about this program, primary objective is to identify and observe asteroids. They have a couple levels of completion, regular 25, and if you're really ambitious, you go for the gold level and you have to observe 100 asteroids. The main thing is to observe the asteroid at least over 2 different occasions and actually sketch the thing, which I do have. There's one of my sketches. Basically, and you can see this is 704 Interamnia. Which I did back in December, middle of December this last year. And basically, observed it one night. You can see the notes I have for this and was able to track. Now this one, you'll notice the power I was looking at. So I was about 51, but I needed my 8 inch.
Pete, if you have another screen you're trying to share, you're only sharing your PowerPoint.
Oh. Can I share two at the same time?
You would have to cancel the share and reshare your
Oh,
whole desktop.
okay, let me do that. Let's do this real quick because I want you to see this. If I could pop it up, where'd it go now? There we go. And I want to share this one. Oh, it isn't going to let me share it. Darn it.
You could then just share the individual app and then share that and talk through that, your notes real quick, and then go back to the PowerPoint as a share.
Oh, I see. Okay, I see what I'm going to do. So, okay, got it now. Figured it out. Now you can see it. Yes?
Yes.
Okay, so this is the sketch. Yeah, this is the rough sketch I made of this particular asteroid, and was done over. I think this one was done on 2 successive nights, approximately almost 24 hours, and I was able to document a movement of about 13 arc minutes, which is pretty substantial. This one showed up, and I can't remember the how difficult it was or what the apparent magnitude was. It wasn't the easiest thing. But in this case, I had a pretty empty field except for 26 Auriga, which helped out quite a bit because it wasn't too far from there. It was very easy to show the change in position. But basically, that part and parcel is what the asteroid program is all about. Oh, I like that. Anyhow, so now let's see if I can get rid of this and go back to some. So I stopped sharing that.
Pete, did you
Go
say
ahead.
arc minutes or arc seconds? Your connotation was arc seconds.
Oh, it should have been arc minutes. I apologize because basically, yeah, that's my bad. I'm gonna have to go back and correct that. Thank you for pointing that out because what happens is you can see I was looking roughly the field of view I had was just under I think it was 0.85 degrees, so that would have been roughly 51 arc minutes. So it should have been arc minutes. My bad. I apologize. Appreciate the correction. Because roughly it was about a quarter of the field that I was viewing with that, with my 8-inch SET with the, I think I had the 40 eyepiece on there. So thank you for that. Appreciate it. But anyhow, one of the sources that I use in this program, the Astronomical League recommends, they have about 10 different sources as far as being able to locate asteroids. I'll probably have to get to those, but one of the easiest that I found for being able to source asteroids is an online source called Heavens Above, and it does a lot of different things. You can track satellites, comets, and a lot of other astronomical bodies and artificial ones too. But for the most part, typically when I go in there, I'll see the table over on the left, which gives me the rough, the apparent magnitudes of a number of asteroids. For the most part. So the one I'm going to be keen on next is 532 Herculina. When I decide I'm going to stay up long enough and get Botes high enough in the sky. But you can see there's the basic, the chart on the left shows a rough, very open field view. So you can see where it lies in the constellation. And then the one to the right shows the asteroid amongst some major stars in some cases. And this is basically a 2-degree view. So it's a little bit, larger than what I would be doing with my telescope, but it gets me in the ballpark, which is kind of nice. And I found this to be very accurate, at least for this particular program. So if you're out there and you want to take a look at some asteroids, and like say about the only one that is probably visible, if you've got good eyesight to the unaided eye, is going to be Vesta. When it's at opposition at 5.1. Sirius is going to be difficult to see. It's just a little bit too dim. Some folks might be able to pick it, but those are about the only ones that can be seen. But the interesting thing about this, you have the asteroid along the left column here, and you have its apparent magnitude in the right. And of course, obviously, some of the bigger ones are not at opposition right now. They're probably, laying off I don't know, either a quadrature or somewhere inside that. And the altitude is what when you query the location board at the time, this gives you the rough altitude above the horizon for any given time. So this will change hourly during the day. It's going to be roughly the same from night to night over a period of time. Of course, it'll change slowly. And of course, you can see what constellation the asteroid is. So if you want to do any asteroid hunting, I found this to be a quick, easy way without having to read some complicated tables to locate asteroids as far as your own viewing goes. Okay, so that was enough about that program. Oh, that's it. These are my references that I used. Thank you for your attention. Are there any questions?
Can you go back to the previous slide?
I can go back to before my references, you mean?
The one that had
That one?
yes.
Okay.
This wasn't mentioned in your notes on naming conventions. The old naming convention, which is what's shown here, is the number in front of the asteroid represents its size.
Yes.
So with one series being, the largest object and then its name.
Right. Thank you. Any other questions or comments? Thank you, Ross.
Would you go back to your references slide?
Yes.
I didn't get a chance to catch all of that. Okay, thanks.
You're welcome.
All right. Flap down.
And although I did mention this in the chat, another resource for observing planning that I use particularly quite a lot is Telescopius, and they recently had an update that included asteroids and minor planet bodies in their tracker. So there is a link to series inside of the Zoom chat for those that make use of this particular tool. I do quite like it, especially for deep sky optics, because it does allow you to get a sense of object framing in eyepieces and cameras. So definitely, it's my personal reference when I plan my observing. Just wanted to share that out. So
Thanks, Connor.
and with that, since it doesn't sound like we have any more questions or comments, that'll go ahead and wrap up this month's meeting. There's a mentioning this for the recording, since I wasn't in place to mention it earlier. We will not be meeting in April. There's the solar eclipse. That's more important. So our next meeting will be in May. I think it's May 9th. Let me double check that on my calendar. Yes, May 9th. And I am at the moment thinking about having that whole meeting be on fast radio bursts, which is a topic that I've been following the publications on this object type as they've come out. It is a very recent addition to our that's weird list of things in the night sky. So I do not know if I will have it in time for May. There will be a lot of me digging around archive.org papers and actual research publications to try to get material on that, because it is very much an area of active research in terms of identifying what the heck are these things.
It's fairly new too, isn't it? I mean, we're talking the past decade.
Past 2 decades, yes.
Oh, 2 decades. Okay.
I think the first observation was like 2006. I want to say off the top of my head. I can't remember. So look forward to that. If not, if I don't think I'll have it ready for time, Pete and Steve, who has already left, I'll probably be reaching out to see if you guys can contribute something if I don't have enough to get through it. So with that, look forward to May. And everyone, hope for good weather if you are traveling for the solar eclipse. And I wish you the best of luck on your observing.
I wonder if we could just ask as a thumbs up or a wave, how many are going to the center line? One, two, three,
Wow.
four,
there's
myself,
probably-
five.
I
If
will be
you
going as well.
if you don't have a camera going, do a reaction with a thumbs up. Okay. Looks like a good half of us, if not more. So excellent.
Friends, this is Charles. I have a question.
Go for it, Charles.
Is the April general membership meeting happening or not happening? I've seen it announced two different ways.
It is not happening.
I was
Not
under
happening.
the understanding that it was canceled.
It has been canceled. And
think
the May
on Tuesday-
meeting is going to be Zoom only.
Okay. I thought it on TucsonAstronomy.org. I think that it's still on the calendar, and that kind of confused me.
Yeah.
But thank you. Thanks so much.
Thanks for pointing that out. I will check that out and I'll take it off if that's the case.
Thanks, Bernie. I was about to shoot an email off to
And
Ed.
Bernie, we're probably
Plug in,
not
I
looking
think
very
Ed
good
made
for
it, so-
Catalina tomorrow, are we?
No, we are not. The ranger just dinged me and asked if I wanted to cancel. I went back to him and said, do you want to cancel? So I don't yet, because I typically do it on the day of.
Right, at about 4-ish, unless it's really bad, you know it's gonna be. Oh, but yeah.
Yeah, exactly. But as I told him, I usually don't do it until the day of. I offered him, if he had to do it for reasons of his volunteers, that's fine. Go ahead and do it and let me know. I haven't heard back from him yet, so good chance though. Yep. you're
Yeah, the
right.
weather reports are still holding with rain starting probably early morning, but it's not gonna be real heavy, but I'm sure it's gonna be overcast all the way through into the evening.
It certainly sounds that way.
Although
It's
stranger things have
unfortunate
happened.
because we were going to do this one last month and it got canceled for rain. So I shifted it to this month and it got us again.
Womp, womp, womp. Pesky weather. I like to sometimes joke, unfortunately for astronomers, we have an atmosphere. Fortunately for everybody else, we have an atmosphere.
Yeah,
So-
it beats having to survive outdoors without a spacesuit, Connor.
Hey, I'm in camps, so.
Okay.